minus v times 1 minus z bar. That is raised to a power, all this power there, gamma prime minus alpha minus beta plus 1. So so the variables that appear in the integral representation are these variables that are not the invariants, but something that you need to square to find a solution of a quadratic equation in order to get them. So they have square roots when you want to express them in terms of the invariants.
Do you remember that, Shi-Yang, is this variable z bar, that z times z bar is p1 squared over, well, here in this case, z times 1 minus z bar is p1 squared over p3 squared. Yeah.
But sorry, it is z bar, or what do you want to? I mean, the way I called it now is z bar.
Yeah. Okay.
Is the invariant. That's p1 squared over p3 squared, and the other one is p2 squared over p3 squared. That's 1 minus z times 1 minus z bar, right?
Okay.
So what Aris is essentially saying is that the last factor in the integral representation, the one that contains the external kinematic variables, it should not be written in terms of a linear combination of the external kinematic variables. Let us look at your representation again. So here, what is your x1 and x2? They are the invariants, p1 squared over p3 squared and p2 squared over p3 squared. So this is not the form that not at all the form that we had when we had the integration between 0 to 1, 0 to 1. Yeah. Okay. No, look, I think that this might be a difficult exercise to begin with. It is difficult. It's really 100% difficult. So I don't want you to spend too much time in something that may or may not work, but since it's very difficult, we don't know what the chances are. So let us try to attack this sort of question in a different way, and here we will try to use not an all-order representation, but an expansion in epsilon. So many things have been done to all orders in epsilon, but really one can infer a lot from the first few orders in the expansion. So I think this can be in some sense a theme in your work, because we pushed quite a lot this integral representations in terms of hypergeometric functions, but we have not exploited what it tells us about the first few orders in the expansion so much. So what you can do is try to do that precisely, and leave the more difficult manipulations of discontinuity in terms of LF4 if you have time later on, or you don't do it and someone else will do it. Okay, I can have a look at it myself. So let's try to go in a direction of expansion. So do you have, I forgot what I've given to you. Do you have the expansion of the Apelle-4 that corresponds to the triangle bubble? To this double triangle? I thought, okay, so let me give to you some expansion that we used in this paper. We're looking at okay. Let's just find expressions. Iris, did I send it to you already?
Yes, I think that's why you might have sent it to me, because you sent me some stuff.
I did send it to you, right?
Yes, but it's on a different folder in the Dropbox.
So can we let's see if I can move it. There is one that's called expression check. No, but what did I send to you? The triangle bubble or the
Well, actually, I don't know which function it is. I just know it has expansions in Epsilon.
No, but let's see. I would like to see which one I sent to you. I mean, no. This is the sunset.
The sunset.
That's too much sunset, I think. I mean, because I see there are 14 integrals. That's not what he needs. So let me share the relevant thing. Just a second. Okay, so now you have something here in the Dropbox. So try to open it. This is just a directory with the files that correspond to the expansion of the first few orders that James has done. And you can check it because it's not been fully checked. Now, what has not been fully checked is the coaction, but I mean, because there seem to be some. Okay, now what you have here, so the first section, if you go above that, is load the data. Okay, no, you don't need that. You don't need that. That you run that, but it's not so. So you see, what it does is that if it sets to the right directory, which currently it isn't, of course, then it would import and give names to the expressions that you have here. What are these expressions? These are the expressions for the masters that are, and for the cuts that are used for this double-edged triangle. So let us look at the the paper again, the recent one, yes, this recent one. So if we go to the double-edged triangle, you can go to the pictures first, so I can show you what is available. What general structure? No, no, to the pictures of the coaction. No, it's section 5, I think. Why is it so slow? Yeah, you go a little bit up and you'll see it. Just a little bit up. A little bit up here. Yeah, you see it. So if you go up once more, you get to the point, or again, one page. Yeah, one more page. Yes, that's it. So you see, this is the coaction. So you have what are the ingredients that we have here? We have two. So we have the integral itself on the left-hand side, and then on the left entry on the right-hand side we have the sunsets. Two versions of them, just with different scale, but these are trivial functions because they are just the scale to a power times some gammas. And then there is the function itself, right? This the one that is in 5, just the last term in the second line is the original integral we started from. It appears on the left entry, and the final thing that appears in the left entry is the other integral, which is also a master integral of the same topology, same top topology. It has all propagators again, but has a different structure. It has a different number of dimensions and different propagators, but the same propagators but different powers. Forgot exactly how it works. Maybe the first one is in 4 dimensions and has a double propagator, whereas the second one is in 2 dimensions and have all the propagators raised to power 1. I think that's the way it works. So anyway, these 2 integrals have been chosen because they are good, they are linearly independent, and they are pure. So once you normalize, they become just pure polylogarithmic functions, okay? At any order. So they don't have any mixed weight or things like that that make them difficult. Okay, so they're easy, in principle, they are easy to expand, but they are Appel-4, they're not that easy. So there are functions of 2 variables, and they're all, and these 2 are Appel-4. Now, now we look at the cuts. For the cuts, the more we cut, the simpler it is. So the last 2 terms that come with the original integrals, they are in turn quite simple, relatively simple. I think there are 2 F1s. So it's 2-dimensional cohomology space. And the other things that we see here, which come together with the sunsets, are a linear combination of the maximal cut and a 2 propagator cut. And that's slightly more complicated, but not very much. So now let's look at the expressions. We expect to have 2 that are called P1 and P2. These are the actual party hat, and then two that are called S1 and S2, that are the sunsets with different scales. And then we expect to see the non-maximal cuts and the maximal cuts of these two. These are all the ingredients. So let's now look at the file and see that that's indeed what we have. So we have, you see P1, P2, these are the master integrals themselves, not cut. S1 and S2, these are the sunsets. And then we have max cut of the P1, P2. There are two maximal cuts because there is two contours, and then for each of the masters, so that would be 4 terms, right? That's the 4 that are listed there. Max 1, P1. Do you understand that? Is it? Do you understand the classification? But yes, yes, yeah. That identify which contour it is, and the our number after P, it tells you which integrand it is. Oh, you know. And then we have triple P1 and triple. That's a triple cut. That's 3 propagators cut, and this is given at the end. So now, if we go. You know, all these expressions, they actually look very similar to each other after the expansion, because after the expansion, they are just polylogarithms of the variables z and z bar, or y and x, depending how you call it. Before expansion, they don't look so similar. So the triangle, because they look, they are Pele 4. So this triangle int that is shown here is taken from an old paper, and it's more general result. So then it is being specialized to the case that we need in 2 different ways, and that defines what is called P1 and P2. So if you go down a little bit. Okay, so that's the party hat integral after specializing some of these propagators. Then you go down more. Okay, now these are still, if you go a little bit up, you see this line P2 minus K to power A, and A tells you is the thing that distinguishes what power you take this propagator. So that identifies the master integral. And so you see that A enters into the parameters that enter into the Apelle 4. So you get different Apelle 4s for different integrands. And then you go down. Okay, so at sunset, okay, here. So we finished with P1 and P2. This is the 2 expressions we have here. And then we have the sunsets, which are really simple. And if you go down more, there would be the expansions. Like, yeah, you can go over how the expansions are done. Basically, they are expanded under the integral and then performed order by order. I'll let you go over that yourself. And then let's go over down to see what is given for the cuts. I think it's another section. So this is the expansion of the master integrals, and the expressions for the maximal cuts. You see that these are simpler functions. What's going on here? I can't see the functions. Go down. No, that's not the final one. Well, it's all commented out. You'll have to uncomment it when you run, and then you'll see what form they take. So let's go back to the paper, and now go in Appendix C. Appendix C, yes. Right. So now let's see how they look before expansion. Yeah, precisely here. So these are P1 and P2 as a linear combination of F4s go down. Okay, that's what I want to show you. You see, these are the maximal cuts. We see that they are here. They are written in terms of F2 functions. But that's go up a little bit. No. The F2 are not the maximal cuts. Go up. Okay. Yeah. This is the maximal cut. You see, it's 2F1. 2F1 is good because that's two-dimensional. Okay. And then if you go down, these are the F2s that you see. F2 is very similar to F4. It's just a bit simpler. And so these F2s represent the 3 propagator cut. So all the expansions are given there. Now, what I suggest to gain confidence in this thing is to try to evaluate the expansions and the integrals. Okay. The integrals, I mean the F4 ones, and the expansion, and the same for the cuts. Try to evaluate numerically. Is it clear what I'm saying? You don't need to expand it. I mean, you can expand it using HypeExp, for example, but you can also rely on the expansion that James has done. It's up to you. Okay. Do you know how to use HypeExp? That's very easy. Yeah, so 2F1, you can expand using HypeExp. Make sure that you write it in terms of good variables, not square roots, before you expand, okay? Good variables would be this Z and Z bar. For the expansion, it's always good to write it in terms of Z and Z bar. Not this Z1 and Z2. Is it clear? I mean, I'm talking too much and I cannot, I mean, okay. Now, how to evaluate numerically the F4? You have two ways. Either you evaluate numerically the integral representation, or you go to Maple and evaluate, and then there is a F4 is implemented there. So I think I can arrange for you access to Maple if you want to do that.
Probably the Maple is the safest bet, because I'm thinking that if there are somehow poles in the definition of the F4, then numerical integration will blow up.
But why do you mean poles? I mean, this is a good function. It has only endpoint singularities.
Yeah, but if you have endpoint singularities and these are not well regulated, then it will blow up.
They are regulated precisely by the epsilon.
By the epsilon, exactly. Sure.
That's the definition. The thing that can happen, that's important, is that you might end up choosing a bad region where the particular contour that you have, particular integration region, includes the pole. I think that's probably what Aris is meaning. So if you have a situation where you choose a bad region, a region where one of the factors appears, as to have a branch point inside the integration, that shouldn't be done, right? Then for that you should, in principle, analytically continue. If you really wanted that region, you should analytically continue and derive another integral representation such that this doesn't happen, right? Okay, when you have particular parameters that you want for your physics, which is certain values that we discussed last time, what is the region of P1, P2, and P3? Once you know what region you are, you make sure that the integral representation is such that there is no branch point inside the region. But in fact, it's best to choose it such that also the F4 has a convergent expansion. And we saw the conditions for that last time. It was that the square roots of the sum of the square roots of the arguments are smaller than 1. Remember that?
Which easily translates to the fact if you choose arguments smaller than 1, then you're guaranteed to lie. No, that's not true, actually.
No, it's not a square. It's a circle in this case.
Yes.
But the other way around is what we discussed last time. So if you go beyond 1, then you're definitely going to make the series divergent. And that's actually what you need to do when you want computer discontinuity. Because what you want to do is you want to go to the region where there is a discontinuity, not the Euclidean region where everything is real and positive. But in the first instance, what I'm suggesting is that you evaluate the integrals, of which we eventually will take the discontinuity in another region. But first, let's evaluate the integrals and gain confidence that the expansion represents the function correctly. Now, what does it mean correctly? Expansion is only valid at a given order in epsilon. So what we need to do is we need to choose epsilon small enough. And epsilon needs to also be negative. If it's not negative, then these integrals are not well defined. It's, for example, these factors that Aris mentioned that suppress the integrand near the endpoint, they have to really be suppressed. To be suppressed, epsilon has to be negative, and that provides an infrared regulator, which is what we need here, because these are infrared divergences. Okay, so you set epsilon negative and small enough, then I expect that you get a reliable result both for the integral and for the series. And you see for the series that as you go to include more orders, you get closer and closer to the result that you get from the integral representation. Okay, so it converges. It really converges in this region. Once you know that, okay, you have control of it in the region where it converges, then you can look at the expansion. And in the expansion, you have polylogs, and polylogs, we know how to analytically continue. You don't need to worry about all these complicated contours, because the polylogs are functions we know how to deal with. Now, There you have another difficulty. It doesn't come for free. The other difficulty is in order to understand what discontinuities you're computing, you would need to analyze what happens when, say, I don't know, P1 squared is larger than P3 squared, and you are out of the region where the integral representation is a good one, and out of the region where, yeah, exactly. So you can still use the polylogs, because the polylogs, they can be easily analytically continued, but they are written in terms of other variables. They are written in terms of this z and z bar that have a quadratic equation solution in terms of these invariants. So you need to follow, what is the region of this z and z bar, and when you take a discontinuity, what happens to z and z bar? Okay, so the difficulty is now in another place, but it's doable. Do you understand what I'm saying? I mean, let me give you an example. In the physical region, where all of these momenta are, let's say P1 squared over P3 squared is smaller than 1, much smaller than 1, let's say, and P2 squared over P3 squared is also smaller than 1. In this region, let's say that are very small compared to 1, it's a Euclidean region where I think the F4 doesn't have discontinuities. And it's not the region where you eventually want to take the discontinuity. Let's see. I mean, that region, for example, can happen. I'm trying to think about the physics situation. Suppose you take all of the 3 scales to be space-like. Space-like. So if they are space-like, there is no discontinuity in any channel. Okay? You never have a situation where you can put things on shell by cutting. All of them are space-like. So all of the ratios are positive, and we also arrange them to be smaller than 1 so that the particular representation we have is easy to evaluate and real. So everything is real. Now, what happens with the expansion? The expansion are polylogs of z and z bar. Okay? But there would be very specific polylogs of z and z bar. I bet they would be, at least for the second master integral, P2, they would be actually single-valued polylogarithms. For example, wait one example, log of z times z bar. That's log of psi, log of P1 squared over P3 squared. If this is positive, the log is positive, and there is no discontinuity, right? So, what was the secret to not have a discontinuity? That z bar was complex conjugate of z. Okay, then both z bar and 1 minus z times 1 minus z bar, they are real, and that's fine, right? But now imagine that now I got polylogs. I got, for example, polylog of z plus polylog of z bar. Okay, example, right? Now I can treat z and z bar as independent of each other, right? I can just evaluate wherever I want. If I take them independent of each other, I can take, for example, both of them real, both z and z bar real. What have I done, actually? Let's try to think about the physics of it. If both of them are real, obviously I'm not anymore in this Euclidean region that I started from, where they were bound to be complex conjugate of each other. I just analytically continued to some other region. Okay. I can be in the Euclidean region, but I may also not be in the Euclidean region. Okay. Because I just analytically continue them separately, and they are not more complex conjugate of each other. Okay. In this case, then you're not going to get a positive, a real value from evaluating these polylogs necessarily, right? And there you can compute a discontinuity. But you then need to know on which variable you compute the discontinuity. Is it on Z or is it on Z bar? For example, where is the cut in these variables, Z and Z bar? So that's what I ask you to analyze. But that's in the second step. So the first step, just make sure you have a good expansion. The expansion has to agree with the original function in a good Euclidean region. Then once we know that we are happy with that, then we look at the expansion, and now we depart from this Euclidean region and allow Z and Z bar to be whatever they like. And then we try to think, okay, if we take P1 large, so that this would correspond to a case where there is a discontinuity, or maybe change the sign of some of them and so on, or all of them. And then we think about that physical situation where there is a discontinuity. Now we would like to find what we have to do with the variables Z and Z bar in the function in order to find that discontinuity mathematically. And we will be able to do that because polylogs are not that complicated. And out of the region that Z and Z bar are complex conjugate of each other, this result is not going to be single valued. It is going to have cuts. Okay? Not sure.
It does sound a bit complicated until you see it, but if you have any questions, it's good that you ask them now, even if you're not sure what you're asking. Even if
you can ask. You can ask now. I think that look, we take it step by step. If you understand what you're checking in the Euclidean region, expansion versus evaluation of the functions, that's already a great step. In fact, you can check each and every ingredient that enters this coaction. Some of them are really simple to F1. Some of them you need, say, maple or evaluate the integral, but you can check them. Once you've checked them, you have confidence of the result. But of course, in a limited region, it doesn't matter. You have confidence in the result. Then you can analytically continue the expanded result. Okay? So let's do the first step. Let's take just the unexpanded integral, the uncut integral, and try to do that. Okay? You can also do start the other way around. You can start from the 2F1, not F4. It's really easy to write in terms of Z and Z bar. It's really easy to expand because you can use hype X. You can do that compared to the expand that James has in terms of Z and Z bar. And then go to a more complicated function, which is the F4, where you have his expansion, but you can also evaluate numerically and check that it all matches. So you can start from the 2F1, which is the maximal cut. The only thing that for the maximal cut, the way it's written, I cannot guarantee things up to I pi. So you see there is a bit less control of the I pi's, which you might be able to settle, but it's for the cuts. Since this was supposed to be understood as right entries in a coaction where additive terms I pi do not matter, then there is some ambiguity of what these extra I pi's would be. But that's a disadvantage. Anyway, to play with the expansion, this is good enough. You can take a 2F1, expand it, and compare to the 2F1 before expansion, see that for small enough epsilon, you have convergence. And once you're happy with that, you go to F4, which is a more complicated function.
And then, if I understand correctly, you're saying set in the expansion the IPIs to 0 for the cuts.
No, so, okay, when you compare the maximal cut to its own expansion, you have to respect the IPIs.
Okay.
I mean, because this is the, just a check of the given expression. Okay. We might get to such issues. Let's postpone problems before, not need to discuss before they occur. Okay. I have to take this just a second. Hello?
I don't know if we're muted. Oh, Inan's going. Okay, good. So yeah, so the idea is for HyperX, you know how to expand it to F1, right? There's no issues with that. Okay. Then for the now we're being muted. Okay, good. For the other one, if you don't want to use Maple, then for the F4, the idea is to use n integrate. So if you write that down, n integrate is what Mathematica uses to numerically integrate a function. So what you do in this case, you plug in the integrand for the F4. You need to choose your, you need to fix your variables essentially. Everything needs to be numbers. So you need to choose numbers for everything. So you will need to choose numbers for P1 squared, for P2 squared, for P3 squared. You have to choose numbers for epsilon as well. Like epsilon needs to be very small and negative. And after you do this, you put n integrate and okay, you still have integration variables and it does the integration numerically. Now, if the answer comes back in red, it means you haven't said something in a good thing and it hasn't counted a pole in the integration. So if it comes back in red, think of why there might be a pole. I'll give an example. If you have a 2f1, so in 2f1, say it's an integral over t. I don't know, it's t, 1 minus t to some power, t to some power, and 1 minus tz, z is the variable, to some other power. Now, if you make the mistake of saying, for whatever reason, say epsilon, so say you have t to the minus alpha, and alpha, and say alpha in this case is, I don't know, epsilon, and you put epsilon minus 1, then surely you will have a pole when t is 0. So it will give you something red because he doesn't know how to evaluate this numerically for t equals 0. And really what n integrate does, it really does a sum. It just does a very small sum. So it sums what you tell it to integrate bit by bit. So it really puts one value of t, another value of t, etc., etc. So if a value of t is 0, then it won't be able to do it because it blows up. Yeah. So you would need to have chosen an epsilon that better regularizes this. So this can happen. So if it happens, make sure you've chosen good numbers for everything. If you use HyperX, then this shouldn't be a problem because HyperX just writes down an expansion. Still, you would need to choose good numbers for the 2f1, but that's fine. Just make sure you choose small epsilon and negative.
Let me, so can you please update me what you discussed? I'm sorry, I had to.
Oh, I just told Shi Yang that for the F4, he can use n integrate from Mathematica.
That's true. That's one possibility. And I think that if you choose in the right region, that should also work for you. The other thing, no, but there is no difficulty to use Maple. It's fine. So it's all up to you. The other thing I wanted to say is that there are integral representations for F4, well, for certain F4 that are in terms of integral over two F1s. So when we look at that, I think it would be good to check whether the particular F4s that you have to deal with, or F2s, by the way, because some of the cuts, the free propagator cuts are F2. Let's check whether they fall in the class that can be written in terms of simpler functions. So, for example, I'm quite I'm quite confident that they fall in the class that at least the P2 falls in the class that can be written as a product of some Bessel functions integrated. So there are some extra representations that apply. And if you work with these functions, then it's good to know that there are sometimes easier representations for certain things. So at the moment I don't need to give you more references for this. I think you have enough. It just you have to tell me whether you want me to arrange the Maple license for you, because then you need to install it, of course, and so on. I need to ask the IT people. In fact, it's not complicated, but because we have these licenses, it's just whether you want it. Okay, yeah. So I will maybe let's see if I can.
Maple sounds like a good idea because it's like it's already in there instead of doing one more step to get there.
That's true. The Appel 4 you can really trust. If you put the right things in, you just get the right number, and that helps a lot. That you can rely on something. I personally very much like numerical checks because you can gain confidence, which otherwise it's very hard. Okay.
Maybe another question of interest, Shiyang, from your experience, how many orders of epsilon do you need to find a good enough answer?
From my experience?
Yeah, because I actually haven't tried this.
Well, that really depends on how small you want epsilon to be. So I typically worked recently with, between 1/10 and 100, and I used 4 orders.
Okay.
But
why can you just arbitrarily make it smaller? Just
good question. So then there are other things. So remember that there is also the kinematics. So if you make it very small, then then there are certain things that happen with the kinematic dependence that make it more difficult. So I forgot the situation that occurred, but it's not good to get it very small.
Okay.
Let me see. Alice, do you also think that that would be useful for you?
Potentially, like we haven't encountered any appels so far. But if we ever look at something that's two scales, that's because we're not doing two scale things, right?
Yeah. I think we avoided it on purpose because we wanted things that are complicated in other ways. And
yeah,
if they are complicated in all ways, then we cannot do anything.
But there are some two scale stuff we can actually look at that potentially not end of the world hard.
Yeah. Okay. Yeah, let me know if you have any need for this maple that. So I send you now some details that allow you to log in, to download on this and I will tell the IT people that you will be using it. And Alice, if you need it, then we can easily arrange that as well. No, I need you to ask again. Not sure that. Yeah. So okay. Let's separate. I think you might be confused about something. What you said is correct, but maybe something was not clear. What we want to compute is, in this case, is a discontinuity with respect to, say, P1 of the uncut integral. We take the uncut integral called P1. It's expressed in terms of F4s. It's also expressed as a series in epsilon with polylogarithms. Whatever it is, this is a function of P1 over P3 and P2 over P3. We can compute its discontinuity in the variable P1. Okay? That's already a kind of a physical object, right? Discontinuity in the P1 channel is a physical object that corresponds to some cross section, something like that, at least. Okay? Now, it's also true that that function, this discontinuity, can itself be written as a linear combination of cuts. That's the next step, which I've not yet discussed, but you have checked that step already for the one mass sunset. Okay? So we would like to be able to write it as a sum of cuts in our basis, but that's next. So far, I'm trying to go very slowly. First, we establish that we have expressions that we can trust. Then we learn how to compute the discontinuities, which we will now do by expansion. That is done, of course, in a specific region. And then only after that, we would be able to get this discontinuity function and compare it to a linear combination of cuts in our basis and establish what the relation is between these cuts and the discontinuity function. Okay. There are separate steps. Okay, so I don't know how difficult each of the steps is. I don't think it should be this time. I don't think it should be very difficult. There is one critical stage where we go from the physical variables, which are the invariants, to the Z and Z bar. And that is a little bit tricky because you need to understand what happens to Z and Z bar, which discontinuity you have to take, and what happens to the other variable on which you don't take a discontinuity. When you do that, that's a tricky thing in this method, but we have to deal with that. Okay, but if you this is just quadratic relations, you'll be able to understand what happens to them. Okay. Yeah, so I think we can finish with this for today, and we might return to the doing it in terms of our PLF4s later on. Okay. Good. Aris, we talk tomorrow.
Yes. Can you remind me the time since you're here? Is it 11 UK, if I'm not mistaken?
It's 10 UK, but
10 UK.
I'm free to do it at 11 if you want. I think it's better if we take more than an hour. It's better that we stay with 10.
Yeah, I just remember 11. I don't have preference towards 11.
Yeah, let's do it 10 UK.
Okay.
If you want, we can even do it 9 UK. That's fine for me.
It's okay. Actually, no, 10 is better.
10 is better. Okay, let's do it 10. That's 12 for you.
Yes.
Okay, so we did 10 UK, and I mean, we cannot do more than 2 hours, but we don't need to.
I don't think we'll need more than 2 hours. Yes, indeed.
Yeah, so I hope, a bit more than an hour is fine.
Yes.
Okay, wow, I hope by tomorrow my throat will be better. So I cannot speak too much. Okay.
Is it because you did karaoke last night?
No, it's Corona.
Oh, no.
No, it's not. Now my daughter, just a second. Oh. We had a scare with my little daughter that had some of her friends test positive, and she was tested several times, and it's fine. My older one flew today, so it was a big stress. She just called me from the airport in London when you were when I stopped. Yeah.
Very nice.
Okay.
Okay.
So yeah. So good luck with it, and keep in touch.
Okay.
Okay. Yeah. Bye.
Bye-bye. Bye bye.